is our presentation, What If, with no question mark. That's Ashlyn.
That's Hannah.
And that's Justin.
And we're answering questions that probably shouldn't be asked. That's a little gift of the... Oh, whoa!
Wow.
That did not...
Oh my God.
That was a good presentation.
Yeah, that's right, guys.
What if? There's the gift.
Alright, and we chose this topic because it kind of relates to everyone in that, like, you know, we all live on this planet, so, and answering cool questions about this planet.
So to start off, we found the volume of the actual Earth, just to, like, be able to compare it throughout our presentation, and we did that by cross sections and then with semicircles, and then got this large number for the volume. And then we calculated the linear speed to compare along the way as well, and got that number.
That'd be at the equator as well.
Yes, yeah. And we did it by a day. Yeah. So then our first question we answer is, what if the Earth's radius were twice as big? And we just kind of like calculate different things to figure out how that would like affect different things if the radius were 2 times as big. So we find the volume by cross sections again, but with a doubled radius, and get this number. I'll compare them in a little bit. And then I did a speed change of the 2 times radius as well, and get a pretty large number. So then the next question is, what if the Earth's radius was half as big? So we're halving the radius this time, and calculate that again. And then the speed change of, or the linear speed of half of the Earth. So then the analysis of the volume changes. So these are the numbers like typed out, so it's a little more visual, of what the actual Earth's volume is. This is the 2 times Earth's volume, and then this one's half. And then we use the formula that Maddie and Claire used yesterday, the percent of volume increase. And here's the percentages, so it's pretty interesting. And then the analysis of the speed changes. So the speed change of 2 times Earth is double what the actual Earth is. And that would, if that were the case, if the radius was 2 times as big of our actual Earth, then the gravity would be twice as strong, and that would affect some things. We would have to be like different. We couldn't.
We couldn't maintain this body
Yeah,
structure.
our structure of our body would be definitely different.
Also, I would not be as tall.
Yeah.
Also, the structure of the planet would be very different. It would eventually kind of flatten itself, so it would elongate at the equator and flatten at the poles. All the water would move towards the equator, so the equator would essentially be all flooded and almost all underwater. The poles would be pretty much the only place that I think humans could live if gravity were to be twice as strong.
So then when, if the radius were half as large, then it would be like the linear speed would be half of what the Earth's is now, and so gravity would be half as strong. And so like plants they could grow like really tall because they wouldn't have gravity like stopping them from growing taller.
We'd also have a smaller atmosphere.
Yeah, so it would affect like our breathing and stuff. So kind of what we found from this is like, because our Earth is how it is, we're able to survive, and like it would be way different if we like had a different Earth.
And so then we started thinking about water, and we kind of proposed the question, what if 50% of the Earth's volume was water? And so how we calculated that was we took our volume that we found in Ashlyn's previous slides, and I multiplied that by half. And so the earth portion, like the land portion and the water portion, are obviously going to have the same volume then if it's 50%. And I then was able to find the radius of that earth portion, and with that, the depth of the water surrounding it by using the formula for volume of a sphere. And so in doing that, I found that the water would completely surround the Earth, and it would be about 583 kilometers deep. And to put that in perspective, Mount Everest is only about 9 kilometers, and so that would be an insanely large amount of water around the entire Earth. And to think of it that way, it would be like taking the Earth as it is now and just kind of shrinking it a little bit and putting water around it. And the way the Earth is now, the atmosphere is only about 600 kilometers high, and so that would almost be putting water all the way up to the top of the atmosphere, the way it is now on the Earth. And we kind of were then thinking that because the water would be that deep, sunlight would not be able to penetrate to the bottom of the ocean, and there would actually be ice, at least on the poles for sure, and in other parts of the ocean as well if there are not vents.
It would be approximately, I believe, 60,000 atmospheres is what we calculated at the bottom of the ocean. Jeremy and I were arguing about it in Litcom, so we're like, might as well figure this out. 60,000 atmospheres, that's 60,000 times the pressure that is currently on us as we just stand here at the bottom of the ocean. So this is mine. What if all the volcanoes on Earth erupted at once? So we said apocalyptic end of the world, of course, which, I mean, it's apocalyptic, but probably not the end of the world yet. So there are roughly 1,500 volcanoes on land. That part's not true. It's on the oceans as well. Sorry, I think I forgot to take that out. But there are an unknown number really below the Earth's oceans. We can't really estimate that. I think we can assume there's at least 1,500 more, but the eruption of these would not be nearly as catastrophic as the ones on Earth's surface. So what we started here with was VEI scales. So that's the Volcano Explosivity Index, which is a way of calculating the eruptions of volcanoes. So each volcano isn't necessarily given a classification. Like Mount St. Helens isn't always going to be, when it erupted in 1980, it was VEI 4. It was a VEI 4 eruption, but it's not necessarily guaranteed every eruption of Mount St. Helens will be a VEI 4. So the way we calculated what these 1,500 eruptions would be is by taking all the explosions from the last 10,000 years, basically, and putting them as a percentage. So there were approximately, well, I believe geologists can agree, it's just about exactly 7,742 eruptions on land in the last 10,000 years that have been classified on the scale. There have been eruptions that have been below this, so they were not classified. But 7,742 in the last 10,000 years, and we took these as percentages. So as you can see, 50%, I don't know if you can read that, sorry, but 50%, about 50% was VEI2 eruption, and then I multiplied it by 1,500 to find the number of volcanoes that would be erupting at that explosivity index. And then I multiplied this here. This is the order of magnitude of the volume of tephra that would be thrown from the volcano. Tephra is ash, rock particles, rock fragments, and any other particles that are thrown from the volcano in the eruption. So this is in cubic meters. So this would be, oh my God, I cannot do math. That's 10,000, that's 1,000, or 1,000, right? That's 10,000, that's 10,000. That's 10,000. So 10,000 cubic meters of tephra at VEI 0. So even that is quite a bit. So then I just wanted to make this easier so then I could add all these up and then multiply by a million. So yeah, it's poor format, but it made it easier for me. So this is the answer then that we got, 1.338 times 10 to the 12th cubic meters, which is the same as 1,338 cubic kilometers, which is an insane amount. Mount St. Helens was 0.25 cubic, that should say kilometers, 0.25 cubic kilometers. Vesuvius was 3.3 cubic kilometers. So this would be orders of magnitude higher at 1,000 cubic kilometers. That was about the same as the Yellowstone caldera that erupted approximately 640,000 years ago. So that eradicated quite a bit of life throughout the continental United States. Such eruptions as the Yellowstone caldera have been known to throw ash to a depth of 1 foot over 1,600 kilometers. So that's like unfathomable, really. Like 1,600 kilometers away, that's like Texas, pretty much. So that'd be a volcano erupting in Minnesota throwing 1 foot of ash as far away as Texas. This is the VEI index, and shows the eruptions in the last 10,000 years. This is the cloud column height, and a bunch of other different categories in the way that they're categorized. These are maps of ash deposits. So it's kind of like a topographical map in that it shows the depth of each of the ash. So this is Mount St. Helens right here. So this is a point where it received not very much ash or a lot of ash. Sorry. So I believe it ran into a mountain range or something there, and it's all forced to the ground. And it's almost like a Riemann sum in a way, in the way that they calculate it. They calculate the topographical area occupied by one of these, and then just add all those up in the estimate. And then that's a volcano. And these are our sources. Oh, there we go.
That would be Justin.
That'd be good.
All right. Brian? We recording the questions?
No.